Today our speaker is David Matejov from Charles University in Prague. David is a PhD student of Igor Karkin, who was also here some time ago. Yeah. So we know him quite well. And today the title of the talk is Extremal Isolated Horizons and the Related 5D Black Holes, which were established jointly with Yuri Podolsky and Martin Schultz. Yuri Podolsky and Martin Schultz.
Thank you for inviting me here, and thank you for giving me this opportunity to have a talk here. As it was said, I will have presentation about my work, which was done in collaboration with Professor Podolsky and Dr. Martin Schultz about uniqueness of extremal isolated horizons, and especially the relation to black holes of type D. Let me first go through the contents. At the beginning, I will slightly talk about isolated horizons. Here I will introduce a couple of definitions to be sure that everybody is familiar with this topic. And this section also serves to fix my notation. Then we will move to axially symmetric case, which is easier to understand, and we can derive some theorems here. And further, we will restrict our attention to extremal isolated horizons, which are characterized by vanishing of surface gravity. And after I will show you our main result here in the section. We will make a little step to the side, and we will look at exact spacetimes of the Petrov type D. And we will especially look at their geometry. I mean, the geometry of the black hole horizon, which is present in this class of solution. And finally, I will try to compare both solutions, and I can tell you that we will map one solution to the another. Isolated horizons were introduced as a quasi-local generalization of the notion event horizon, which is not very suitable in many applications because it requires the knowledge of the whole space-time. So it is much more advantageous to work with the notion which is defined quasi-locally. This framework, or the work in this framework is very useful to use for this work is very useful to use the Newman-Penrose tetrad formalism. Let me denote my bases by these four letters. So it's L, N, M, and M bar. This is my notation here. All these vectors are null, and these two vectors M and M bar are complex. So after we introduce this tetrad formalism, we can approach the first definition, the definition of non-expanding horizon. So we say that the
non-expanding horizon is a property of space-time itself without Einstein equation. Okay? Einstein equations are not necessary to define an expanding horizon. But in this definition, you need Einstein equations because we need to assume more than written in those 3 points. If you want to define geometrical without, but we prefer such a definition.
Okay, for me. Okay, for me, this definition is the usual one which I found in literature. But I know that currently there was much progress in this direction, and some of these assumptions can be weakened. For example, you don't have to assume Einstein equations, as you pointed out. Okay, so for me, this is just the definition which I'm used to. And okay, let me define the non-expanding horizon in the way I'm accustomed to use. So we say that the submanifold H of M of this spacetime M and G is a non-expanding horizon if the following three conditions hold. So the first one is that L is a null hypersurface with this topology R times S. So we can think about it as a horizon with a spherical cross-section, basically moving in time. Second requirement is that every null normal to this horizon has vanishing expansion, which physically translates to the condition that the horizon does not expand or shrink in time. And the third one is rather of technical nature, I would say, and we require Einstein equations, in my case, satisfied on H, and the energy momentum tensor of matter is such that for every future normal vector L, this projection vector is also future pointing. As it has already been pointed out, some of these assumptions can be further weakened. For example, I have an example that the topology can be a little different. We can assume that the topology is R times K, where K is compact manifold. Or you don't have to assume Einstein's equations to be valid on the non-expanding horizon. These geometrical properties of non-expanding horizon are captured in these spin coefficients. So by definition, we have zero expansion, but it can be shown that shear and twist of the null congruence is also zero on the horizon. Okay, now we move to another definition of a weakly isolated horizon, which is a pair of a non-expanding horizon and this equivalence class of null normals, which is defined here, and basically it consists of all vectors proportional to L via positive function. And we require this condition to be satisfied, so we have a commutator of the Lie derivative along L and the induced covariant derivative on the horizon acting on L, and we require this to be zero. This condition is more or less gauge fixing and does not restrict the geometry directly. And we can show that for every weakly isolated horizon, the zeroth law of black hole thermodynamics is valid. So when we define a surface gravity in this way, so that's basically acceleration of the null congruence along the horizon, we can show that this quantity is constant.
So you normalize the two way, normalize the one or nine?
Well, that's a good question. Well, in one convention, you can normalize them to be one, or in another convention to be -1. And I think that our convention is such that L times N is 1. Okay. And now we approach the final definition of the isolated horizon as a weakly isolated horizon, where we now require a similar condition to the previous one, but now we require that this commutator acting on every tangential field to the horizon is zero. So now this condition is non-trivial and it restricts geometry. And the restriction is such that the free data, which are captured in spin coefficients lambda and mu, are time independent. So their derivative along the vector L is zero on the horizon. And for our work, we really needed both of these conditions. So we really needed to work with the isolated horizon. Oh, okay. Let me restrict my attention to axially symmetric isolated horizon because, as I said, it is easier and more convenient to work with axially symmetric case, and we can derive explicit results in this case. So let us consider a spherical-like cross-section of the horizon, which can be illustrated as in this picture on the right. And we say that the horizon is axially symmetric if there exists a Killing vector field with closed orbits with non-vanishing norm or with norm which does not vanish only at 2 points, or sorry, the norm vanishes exactly at 2 points. Otherwise, there are no points where the norm is 0. And these points we call poles, the southern pole or northern pole, respectively. Further, we can derive that there exists a suitable, or we can introduce suitable adapted coordinates zeta and phi on this spherical like cross section in which the metric has this special form. The metric depends only on a single function, f zeta, and only one parameter which is related to the surface area of the horizon via this formula. So the metric is quite simple, and it is parameterized basically by one function and one constant. As I already mentioned, extremal horizons are defined by this condition of vanishing surface gravity. They are defined uniquely, even though there is freedom in rescaling the generator of the horizon, which also rescales the surface gravity, but in this case, they are defined uniquely. And our main motivation for this work was the theorem which was proved by Professor Lewandowski and Pawlowski in 2003, I think. And it says that for every axially symmetric, extremal isolated horizon with regular axis, its geometry is isometric to the intrinsic geometry of the Kerr-Newman black hole. Recently, there was much more progress in this topic, but this is what was our main motivation when we started to study this problem 2 years ago. So our first question was if we can find another solutions in this formalism, and or for example, if we can identify the structure of the horizon which appears in the symmetric or, for example, in tau-NUT spacetime. So the idea was such that we relax the regularity condition, which is assumed at the poles. So we will consider a little different topology to the standard one, which is assumed in the formalism. And the second question was if we can include the cosmological constant in the formalism. And as I will show you during my talk, both of these questions have positive answers. So we were able to either identify the structure of this general or different spacetime, and we also included the cosmological constant. Why do we consider extremality in our calculation? Because in the extremal case, some of the Ricci identities and Maxwell equations of Newman-Penrose formalism can be explicitly solvable. So let me start with the case where we have zero cosmological constant, because it is easier and we have a better intuition what's going on. Well, at first, we have to look at the electromagnetic field, which is determined by these three tetrad projections. And it can be shown that on every isolated horizon, the first projection, phi 0 is 0 on every isolated horizon. And then we will assume that the electromagnetic field shares time independence with the gravitational field. So we will assume that the derivative of phi 2 along L is 0 on the horizon. So in the end, one of the Maxwell equations is reduced to this simple equation. And as you can notice, this term, which is proportional to the surface gravity, vanishes in the extremal case. So we have an ordinary differential equation for phi 1. In the previous equation, that was necessary here. It is necessary to derive the form of the spin coefficient pi. So we looked at the equation which governs the spin coefficient pi, and it turned out that the pi can be found explicitly in the extremal case as well. Let me just notice that this operator here is the spin lowering or spin raising operator, but its form is not necessary to write here explicitly. So in the extremal case, we were able to find solutions to both equations, which are written here. And these are very, very simple solutions. Here we have two integration constants, C pi and C phi. And the constant C phi can be identified with total electric or possibly magnetic charge Q defined by the Gauss law. And the constant C pi is related to topological characteristics on the horizon, as I will show you later. So the relation between the constant C phi and the total electromagnetic charge is this one. So this Q contains both the electric and magnetic charges. So there are two parameters combined in one. You mean this is a relation? Or this relation? So the pi solves this equation, and phi 1 solves this equation here. So this is the Maxwell, one of the Maxwell equations, and this one is one of the Ricci identities in NP formalism.
F is still arbitrary.
Yeah, our F is still arbitrary function. Okay. And now we get to the main point, namely that we have two other equations which contain spin coefficient pi, and this projection of wild scalar psi 2, which can be eliminated from these two equations. So in the end, we have an equation which governs the metric function f, which appeared in the canonical form of the metric. So combining these two equations, we get this longer equation here, which is a linear differential equation of the second order with non-constant coefficients. Fortunately, fortunately, this equation can be solved explicitly, and the general solution reads like this. Let me point out that we already assumed that this function f is 0 for the values of psi plus or minus 1, which agrees with the general construction that the Killing field defining axial symmetry vanishes at the poles. And this function f is basically a second power of this Killing vector field. So we already used both boundary conditions to fix integration constants from this equation. Further, we can impose generalized regularity conditions at both poles. Here we introduced these so-called deficit angles around the poles, and we can recast using this condition the previous expression for f into this form. So it's a simple rational function depending on 5 parameters. The 2 parameters are introduced in these generalized regularity conditions and represent the deficit angles. And 1 parameter is related to the area of the horizon, while 2 parameters are related to electric and magnetic charges. So we have a 5-parametric solution, family of solutions. For a special case with regular axes and 0 charges, the function f is reduced to this simple form. And it can be shown that this is a function which describes geometry of the extremal Kerr black hole. Okay, now we move to the case when we are in the ADS spacetimes. So the cosmological constant is non-zero. The construction works also for every value of lambda, so we don't have to assume that it is 0. What is interesting is that the constraints governing the spin coefficient pi and the projection of the electromagnetic field tensor phi1 are not affected by this choice, and therefore the solution is the same. However, the equation governing the metric function f is not the same anymore, but we have here an additional term which is proportional to the cosmological constant. Of course, this term is a bit complicated, but still we can find a solution. And the general solution of this equation can be written again as a rational function, but now a little more complicated. So we had to divide it into 2 pieces, and we had to introduce these constants just to be able to write it in a human readable form, I would say. So this is our main result in this isolated horizon framework.
And compare this with the leading review of
Oh, well, we tried to compare both results in our second paper, and I have to say that they have the result, but the result is very difficult to handle because they use, I don't want to say the weird coordinates, but they use coordinates which are defined not very conveniently. For example, one coordinate is defined, or the range of one coordinate is defined by roots of a polynomial of higher order. So in the general case, you cannot find roots explicitly, and you have to integrate from one parameter to another parameter. And it is absolutely not clear what the 3 parameters in their theory are, what they are related to. So we managed to prove that our solution is equivalent to their solution in a special case of one of their constants 0. When we choose one of their constants to be 0, we restrict the theory, but we manage to somehow map these solutions to one another. But in the general case, it was impossible because of this complication with roots and so on. So yes, they have the result, but I would say that it's not very usable.
And this is published.
Yeah, this result is published in our second paper from 2022, I think. It is already something like 1.5 years ago. Well, In the special case when lambda is equal to 0, this solution is reduced exactly to the previous one we obtained. And in the case of regular axes, when both deficit angles are 0, we obtain this form of a metric function, which can be identified with a function describing geometry of Kerr-Newman de Sitter black hole. And Professor Lewandowski, this result should be familiar to you because you already published a similar result with Eric. Okay, now let me discuss the type D black holes, which are represented by line element of the so-called Plebański-Demiański solution. So it is type D of Petrov classification, and it is a general family of black holes with electromagnetic field which is not null and is aligned to the principal directions of Weyl tensor. This family of solutions depend on 7 independent parameters in general. They represent mass, electric and magnetic charge, rotation, acceleration, the NUT parameter, and the cosmological constant. The line element can be written in this form, where these functions here are functions of these parameters and the corresponding coordinates. And they are a bit complicated, so I don't want to write it here because it's not necessary. In the class, there is also a twist parameter, which can be chosen freely, but not in the sense that it is completely free, but we have to choose it suitably to get reasonable limits. So it's not absolutely free. Well, the horizons are located at the values of coordinate r, which satisfy this equation. And in the general space-time, there are 2 possibilities. So we can get either acceleration horizons, black hole horizons, or cosmological horizons.
What's the acceleration of the sense of they are like it?
Well, I think that this word is related to my calculation when I try to calculate their geometry. The metric function turned out to be 0. The metric function f turned out to be 0. So
I see that those acceleration horizons, but they are the planes.
Yeah.
I mean the section is plane, so that's why the spherical coordinate.
Yeah, I would say yeah. And concerning these cosmological horizons, they are infinite, and they can be recognized in the calculation by this condition. When you calculate surface area of a black hole horizon, you obtain a number, a finite number, while here you obtain infinity. Yeah. Okay, I will show you the calculation and you can tell me what's wrong about it, because I don't think so. Okay, let me continue. Extremal black holes are characterized by degeneracy of their horizon. We can imagine it in the case of rotating black holes when we have 2 horizons, 2 black hole horizons, one outer horizon, one inner horizon, and we are increasing the rotation of the black hole in such a way that they come closer and closer to each other to the point when they merge and form a degenerate horizon. In the case the black hole is extremal. For this combination of parameter, when at least one of these parameter is 0 and lambda is 0, we have this simple position of the horizon, so it is just RH is equal to M. And this is the condition of extremality. In other situations, it is much more complicated. We started with the NP tetrad adapted to principal directions of the Weyl tensor to obtain the result, which is suitable for our investigation, because it is not possible just to take the line element and extract the metric function from it, but we had to do a series of coordinate transformation to agree with the general construction and the theory. Mostly minuses. Mostly minuses, so it's 1 minus minus minus. So we have the opposite one to the standard one in general relativity. So we can find adapted coordinates VR zeta phi, in which the rescale normal to the horizon is just the partial derivative along V. It is null, expansion free, twist free, as it is required by the general theory. When we define the surface gravity by this equation, we can find it, and it is equal to this formula. So it contains the derivative of the function which determines positions of the black hole horizons, or the horizons in general. After the series of transformations, we obtained the canonical form of the metric, from which we were able to extract the metric function f. And the metric function has this simple form. However, these functions appearing in the fraction here are, again, a bit more complicated, and they depend non-trivially on other coordinates. So far, we haven't imposed extremality, so it's just another condition which have to be taken into account. And now the natural question appears if we are able to identify both sets of solutions, especially if we take the function, the metric function from the isolated horizons and the metric function from this Plebański-Demiański class. We can ask if there is a map which maps one set of parameters to the another set of parameters, and if they describe the same black hole. And I will answer this question a bit later. Boundary conditions for these metric functions, are naturally satisfied, so it is 0 at the poles because the function b in the denominator has this special form. And we were able to derive the full expressions for the deficit angles around poles. So they are written here, and by a suitable choice of this free conicity parameter, which we introduced along the calculation, we can regularize one of the poles. For example, in this case, we can choose C to be 1 over 1 minus A3 minus A4. So the deficit angle delta plus is equal to 0. But it cannot be done simultaneously, as it can be shown from these two equations.
So, sorry, the metric comes with some parameters.
Yeah, 7 of them.
So where are those parameters?
These parameters are hidden in this combination A3, A4, and also here in RH, because
And L is not.
yeah, L is the NUT parameter, A is the Kerr parameter. The others are hidden here, and this A3 and A4 are, again, quite long, complicated expressions, and it is not necessary to write it here because it would be very long and not very clear. So let me remind you the function from the isolated horizons. Here we denote it by q squared, this combination of parameters. And when we look at the dependencies of these two functions, as I already noted, the function from isolated horizons depends on 5 parameters, while in the case with cosmological constant equal to 0, the function coming from the Plebański-Demiański class of solution depend on 6 parameters, plus we have one additional constraint of extremality. We divided our investigation to 3 natural subclasses. The first one represents non-twisting black holes when the Kerr rotation and NUT parameter are both set equal to 0. The second class consists of non-rotating black holes with non-zero NUT parameter but 0 rotation parameter. And the third class contains all parameters which are there. Well, the first class is a generalization of Reissner-Nordström solution to acceleration. Here we call this class non-twisting because the congruence of geodesics is non-twisting. The twist of the congruence is characterized by the 3 parameter omega, which are introduced at the beginning, and it is 0 in this case, so it's non-twisting. The horizon is located at the position RH equal to m, and the condition of extremality has this simple form. We can calculate deficit angles directly, and we see that they are non-zero. When we combine them in such a way that we subtract one from another, divided by this constant, we can find that this combination is proportional to m and this alpha. So we can identify it or interpret it as a Newtonian force acting on a black hole. So the difference between these 2 deficit angles is something like tension, and it is accelerating the black hole to one or another side, depending on the side on which of these 2 deficit angles is greater. Here in this case, the metric function is quite simple, so it has this simple form. Let me just point out that this conicity parameter C is free, and it can be chosen in a suitable way. The metric from isolated horizons, which is suitable. Yes. There is only acceleration, so it corresponds. Yeah. There are conical defects because there is acceleration, so it is like charge symmetric. The metric function from isolated horizons representing this type of solution is written here, and we can identify both functions when we choose the parameter q in this way.
What about the phi function?
No, sorry, maybe it's just a bit confusing. This is a number.
No,
Phi.
but don't worry. I know that this phi is real. But I was talking about this function phi.
Yeah.
And this function is also describes the extremal horizon. It describes this rotation. So my question is whether you present here only the solution to the metric thing, but what about solution for phi? Or for this one for the phi?
Well, I think that it's not so complicated to derive it because we already have the general form of pi. It's just, second root of f times a fraction. But we didn't consider it important to write these solutions explicitly.
Okay.
so I don't have it.
Is that I'm curious whether it is one form given by I also has some singularity on one of the poles or not.
Well, honestly, I don't know. Let me think about it. We can discuss it later because I didn't derive this result explicitly. Okay, let me continue. We can match both functions when we choose the parameter q of this metric function coming from isolated horizon in this way, or explicitly, we just rescale the charges, electric and magnetic, by this chronicity parameter, which is free and eventually can be set equal to 1. So we were able to find a relation between these two functions, and this relation is not dependent on coordinates, so it is just the same function parameterized in a different way. We can go to non-rotating black holes, which are a different and interesting class of Plebański-Demiański family of solutions. I would say it is interesting because when we assume that the acceleration and NUT parameters are there, but there is no rotation, the acceleration parameter can be set to 0 without any loss of generality because it's pure gauge. So when we assume accelerated NUT black hole, it's not accelerating. This solution exists, but it does not belong to the type D spacetimes. Again, we can look at the position of the horizon and the condition of extremality, and we can calculate deficit angles, which are in this case characterized by these free conicity parameters. So we get a metric function of quasi-regular sphere, quasi-regular in the sense that we can set C equal to 1 and we have the metric function of regular sphere. It can be easily recognized when we set this zeta to cosine theta squared. So, cosine theta and this square power should be here inside the bracket. The metric function from isolated horizons has this form, and again, we can find a map between these two functions when we choose a q squared equal to 4 pi c, which leads again to the direct relation between geometrically defined electric and magnetic charges and the charges appearing in the Plebański-Demiański metric. More interesting case is this general rotating class of black holes, because it includes several well-known. Sorry? Yeah. From the Plebański-Demiański, yeah. From the isolated horizons.
Yeah, but
well, basically, from the general formula, I have. It is basically this function. Give me a second. Yeah, it's this function when you substitute for these deficit angles and simplify it. Very interesting.
Then the type D spaceline, it looks like opposite. Oh, but okay, this is not rotating.
This is non-rotating case. And
okay, but still in non-rotating case, on one hand, there is only the single function fd, and on the other hand, there is some bigger family, I mean, single of the proportional parameter, and downstairs is the two parameter.
Yes, and that's the reason why we have to find a specific value of q of this parameter. Yeah, q is electric charge divided by area. So it was defined. Yeah, of course, because we are working in the Plebański-Demiański class of spacetimes.
Surprising that there are
Oh, the general way how we approach the problem was that we derived a metric function from isolated horizons, which is dependent in the case where lambda is equal to 0 on 5 parameters. So it's a 5-parametric family of solutions. And we did the analogous thing in the case of these exact spacetimes of type D. So we derived the metric function from them. And this metric function, in the case where lambda is equal to 0, depends on 6 parameters, but we have one additional constraint which says that our metric function comes from the extremal horizon. So basically the set of parameters are of equal size, 5 and 5. And what we wanted to do, we wanted to compare both solutions to obtain physical interpretation of the parameters involved in the Plebański-Demiański and vice versa. So the general way how to do it is that you take a specific case like the non-rotating black holes. Here, you calculate position of the horizon and condition of extremality. You calculate deficit angles. You substitute it to the general formula for the function fd, and it is somehow simplified. In this case, it is simplified just to this simple formula, which depends only on the free conicity parameter c. And you can do the same thing with the function coming from extremal horizons, that you take this expression for the deficit angles, you substitute it into the general formula, you simplify it, and you have some function which depends on the conicity parameter here and the remaining parameter q squared, which has to be found in order to obtain the same function.
So in the case of the type D, in this case, you assume that so this only that the angles are the same. So this is applied to which, to FE or to F isolated horizon?
To both.
Both.
Both of them. Because we assume that these deficit angles are invariant characteristic of the spacetime. So we can calculate them in the Plebański-Demiański solution. So we can directly simplify the function from Plebański-Demiański solution, but we can also use this prescription here in the isolated horizons, and we can simplify the function correspondingly. But the only non-trivial thing here is that we still have this parameter, which in the end is just a rescaling of the electric and magnetic charge, but it is not always just this simple relation. We will see that for general rotating black holes, this relation is not simple like this one anymore, but it's much more complicated. And in the case with cosmological constant, this relation is even more interesting because this conicity parameter has to be fixed to a certain non-trivial value. So basically you obtain a non-trivial relation between the parameters entering the metric of the Kerr solution and the electric and magnetic charges measured by Gauss' law. So I would say that this relation is really non-trivial. Only in these cases it can look like something obvious, but not in the general case. So let me discuss the general case of rotating black holes. As I mentioned, it contains, for example, Kerr-Newman-NUT black hole or Kerr-Newman black hole. The extremality can be related to the rotation of the black hole, so we can relate it to the parameter A. An important relation due to extremality is this condition for the specific combinations of parameters which appear in the function A3 and A4. And this relation allows us to factorize this polynomial and use it in the calculation for the metric function. Now the horizon is located at the coordinates RH, which are not simple anymore. It is not equal just to m, but it's much more complicated expression. And the metric function for this general rotating black hole is this one. So this one comes from Plebański-Demiański. And it is still expressed in the parameters RH and this A4, because otherwise it would be very long and very complicated to be written here. Also, we introduced this arbitrary auxiliary parameters C0, C1, and C2 to have a compact form of the function. And now the identification with the isolated horizons is possible when we choose the parameter q squared in this way. So now the relation between physically defined charges by Gauss' law and the charge parameters entering the metric is not simple anymore, and it is like this. So we have a non-trivial relation between those two sets of parameters. But still, it is possible to map one solution to another because this relation does not depend on the coordinates. So it is just a reparameterization of the same function, which is important. It does not depend on the coordinates. And now we can move to the solutions with cosmological constant non-zero. Yep.
So when you say, so here you compare something with something else? Or...
Yeah, that's the same logic as in the previous two cases when we wanted to compare this function to the function coming from the isolated horizons. And they are the same. I mean, this function is exactly the same as coming from the isolated horizons, provided we choose the parameter q squared in this way, which leads to the non-trivial relation between the electric and magnetic charges. If you have q squared 0, it means that you don't have charge. So you have not charged black hole. So we wouldn't be able to compare those two functions because they would obviously represent a different black hole. One would be charged and the other would have 0 charge.
I mean, it's a special case.
Yes, sure. So then you have what you have. You have Kerr rotating black hole with NUT parameter and acceleration. Yes, it is possible that there is a 0 charge, but I'm not sure what you get. I think that you can directly set q is equal to 0. Yeah, in this case. So when you set that q is equal to 0, you would obtain that you would obtain an additional equation. So you would have 0 here and this relation on the right hand side here, and you would be able to calculate, I don't know, something from it.
So my question is whether you have so what I understood is that you take so it's easy to take horizon of Kerr-Newman or Kerr-Newman-NUT spacetime, and then identify it with your function obtained just by solving the extremal equation. However, can you also do the opposite? Can you take a different solution of the extremal equation
so you are asking if this map between the two sets of parameters is one-to-one. Honestly, I don't think so, because you can have various spacetimes with the same geometry of horizons. For example, in the previous case here, you have NUT parameter and electric charges, but you don't recognize it when you look only at the metric function. So here in this case, we have non-trivial NUT parameter, but how do you know it when you look at this formula? It's not obvious.
Yeah, that's why I have to.
So you can recognize it from pi.
Well, I mean, pi contains more information. Okay, don't worry. Go ahead. We can solve it later.
Yeah, sure. So I would say that in general, you cannot go the other or the opposite direction, because many physical situations lead to the same kind of geometry. Okay, now I wanted to discuss the case when lambda is not equal to 0. But how much time do I have? I don't know. I have something like 5 slides to the end. Okay, thank you. The comparison is very difficult in general, so we concentrated on a special case of non-accelerated black holes with this alpha is equal to 0. So we worked with the very well-known Kerr-NUT ADS spacetime. The condition of extremality in this case implies this relation between mass and the coordinate of horizon. And it is advantageous because it is proportional to HR. So when I did the calculation, I found a trick how to solve it, and I substituted back to some equations, and I obtained big quadratic equations. So that's the reason why we had to restrict our attention to alpha is 0, because otherwise we would have to solve a polynomial of 6th order, and that's impossible in general. Okay, this relation allows us to find positions of horizons explicitly. So we have 2 possibilities. And this first possibility represents the black hole horizons, while the second possibility represents the cosmological horizons. How do we know it? And here we go back to our discussion from the beginning. We can calculate the surface or the area of the horizons. And in the first case, we obtain this expression. So when lambda is equal to 0, we have this simple form, while the other one leads to this expression, which diverges as lambda goes to 0. Yeah. So I would say that it expands to infinity when you go to smaller and smaller lambdas. The metric function of non-accelerated black hole for non-zero lambda can be written in this way. And identification between this metric function and the metric function from isolated horizons is possible and leads to a non-trivial relation between electric and magnetic charges defined by the Gauss law and electric and magnetic charge parameters from the metric. This relation is simplified to this direct proportionality whenever one of these 3 parameters is equal to 0. So either lambda, alpha, or L is equal to 0. But what I think is very interesting is the special case of Kerr-Newman ADS black hole when the NUT parameter is equal to 0. The previous function is simplified to this one, but around the poles, there remain a non-zero conical singularity. Both deficit angles are same and are given by this formula. So in order to have a regular spacetime, we have to choose this free conicity parameter in this way. So it's not free anymore, but it has to be set to a specific value to obtain regular spacetime. And here we go to proportionality between the charge parameters, but in this case, C cannot be set to 1 as in the previous cases, but it has a specific value. So I think that this relation is very non-trivial, and it depends on the cosmological constant of the spacetime. Let me now conclude my talk. So we derived the most general 6-parameter solution for isolated horizon or ADS backgrounds. We identified this solution with the black hole in the general type D class of spacetimes known as the Plebański-Demiański solution. We were able to recognize 3 types of horizons. We found their positions and analyzed their properties explicitly. And finally, we found relations between geometrical parameters from the isolated horizons and physical parameters coming from the Plebański-Demiański metric, and we clarified their interpretation in various special cases. Here, I would like to point you to our 2 papers, on which this talk is based on. And here we have other references which I used during the talk. And that's all. Thank you for your attention.
I ask you any questions?
Can you somehow summarize what is the main result? Because it was not easy to follow all the details in the calculation. What do you think? What is the main result?
Well, I would say that there are 2 main results. One main result is that we were able to find the general function describing the isolated horizon in our setting. That's the first result. The second result is that we found an analogous result from the type D metric, and we were able to identify it with the previous case of isolated horizons. So we were able to find a relation between geometrical parameters and physical parameters of the metric. So I would say that one is that we derived this.
Okay, so we have some general solution, maybe 6 parameters or 7 or whatever, which governs locally null set.
Yeah.
But all of them correspond to space-time which are type D, or there are some other horizons which are not type D. So there is no Einstein equation solution which corresponds to this horizon. Have you any such result?
If you mean the case of isolate.
Not with some geometry.
Okay, I think that the result from isolated horizon is much more general than just the one derived from Plebański-Demiański. And it can be shown that it is always of type 2 or D, I think. But it can happen that you can have an algebraic, well, you can have a spacetime of algebraic type 1, which is a generalization of Plebański-Demiański class. Actually, it was shown recently that such a spacetime exists. And you can have a black hole there. You can do the same calculation, but I think that the function which comes from the extremal isolated horizons will be the same, and it will be capable of describing the horizon of that black hole as well. But in our case, it happens that it is possible to identify it with just type D black holes. But in general, it's much more okay, general.
Are there questions for from Zoom participants? Yes.
There is one online participant.
But they are not visible and we cannot hear them either. So okay, so let us think this here.